Hi, everybody. My name's Dr. Nick Bonne. I'm a Public Engagement and Outreach Fellow at the Institute of Cosmology and Gravitation at the University of Portsmouth in the UK. And today I'm going to talk to you about the Tactile Universe project, which is a project that we run here where we're looking at ways we can communicate topics in astronomy to blind and vision impaired people. So I'm going to be talking a little bit about the project, the resources that we've created to communicate astronomy, but also how we've worked with the blind and vision impaired community to develop those resources and make them really versatile. And then I'll finish off by talking about how we actually deliver our resources to young people who are blind and vision impaired in school settings. So I always start these talks off with a statement, and that is that I think you'll all agree with me that astronomy is a really, really visual science. The way we do our research, the way we talk about astronomy to people, the kinds of things we use to get people excited about astronomy, all those beautiful pictures of space, are all really, really visual. And so what do you do if you can't see those images? How do you actually access astronomy? How do you feel the same wonder and sort of passion for space that somebody who can see those images is able to? So back in 2016, we started the Tactile Universe project. It's a project where we take real data, turn it into tactile resources that can be felt as well as seen, and we use that to communicate with blind and vision impaired people, tell them all about current topics in astronomy and astrophysics. The project actually started because I'm a vision impaired astronomer myself. Obviously, my journey to become an astronomer wasn't always particularly straightforward, but that's a topic for another talk. But somebody sort of asked me, what could you have done to make becoming an astronomer a little bit easier for yourself? And my sort of almost instant response was, well, if we could make everything tactile, it would have been so much easier. I wouldn't have had to try and look at all the images that I needed to study as a part of my PhD. So the main goals of the Tactile Universe project are really to work with the blind and vision impaired community as much as possible to create accessible resources that are versatile and quite usable. We then want to make sure that we deliver those resources to young people to raise their aspirations, to inspire them with space, and to show them that topics around astronomy can be accessible, that we might just need to think outside the box and do things a little bit differently. A big part of the project is also raising awareness about accessible approaches to science communication. So we do a lot of work with other science communicators, with other researchers, to show them the work that we're doing, but also help them make the work that they're doing more accessible in lots of different ways. And last but not least, we really want to show everybody that accessibility helps everyone. So even though you might start off designing something that's going to be accessible to people who are vision impaired or who have hearing impairments or any other kind of disability, usually you end up creating something that's more accessible for everybody in the process. And hopefully during this talk, I'll show you how that works. So yeah, one of the biggest problems we have in astronomy and the way we communicate it is we tend to rely on really beautiful pictures of space like the one I've got here. And so this is the galaxy Messier 51. It's a face-on spiral galaxy. You can see just looking at this, there's a striking amount of detail. There's lots of different colors involved. There's all kinds of beautiful detail in the spiral arms as they wind out from that bright yellow central core. You can see detail that looks almost like feathering in those arms where there's lots of gas and dust and new stars being formed. And you can imagine if you can't see this image, it takes a lot of words to actually describe what's going on. So our simple solution to this was to make a tactile surface that basically communicated all of that detail, but in a way that could be felt rather than seen. So on the left, I have a telescope image of Messier 51, and on the right, I have an example of the tactile surface that we create. And so we originally make these in 3D software called Blender, and then we're able to 3D print them. So there's something physical that people can interact with. And the way the software works is it basically looks at all the pixels in the image. It takes the brightest pixel and makes that the highest raised point or the highest tactile point in the image. It takes the darkest pixels then and makes that the lowest point or sort of the base of the model. And then it scales all the other shades of gray in between. And so what you end up is sort of almost like a topographical map that you can run your finger across or run your hands over, and you can feel that parts of the image that are bright, the parts of the image that are dim. You can feel the shapes that you would be able to see if you were looking at this image. You can get a sense of what's going on in that image of something like a galaxy. So we realized very quickly with this project that co-creation really had to be an element. So we'd obviously come up with a good idea, but we only really had my perspective on how things should work. And so I'm only one vision impaired person. My experiences are going to be very different from everybody else with a vision impairment. Everyone else with a vision impairment is going to have their own unique needs, things that will work better or won't work so well for them. And so we realized really quickly that, yeah, talking to as many other people who are blind and vision impaired to get their feedback on things and to get new ideas was really, really important. And this was definitely the result of this, I think. We were able to make our models much more versatile. The people we work with suggested things that we would never have thought of on our own. I think that's been really crucial to the project. So in our initial pilot phase in 2016, we created lots of different versions of the models that were different sizes. We created models that had different tactile heights to see what was going to work the best for the largest number of people. And we took those models out to talk to local students, to talk to people who were part of sort of blind and vision impaired support groups. We got as much feedback as we possibly could. And so we were able to settle on parameters that worked for the majority of all of these different people. We also realized very quickly that no matter how good your models are or the resources you create, if you don't pair them with good descriptions and good language that's accessible, then the models don't really mean very much. So we did a lot of work as well where we actually went out and talked to people, showed them the models, asked them whether the language we were using to describe them made sense. And if it didn't, then we worked backwards and forwards with them to sort of find the best way of describing something that would work for a non-visual, or I guess a less visual audience. So the models that we settled on look like this. So on the left, I have the front of one of our tactile models where you can see the 3D printed surface. And then on the right-hand side, I have the back of one of our models where you can see something that looks a little bit more like a traditional photo. And I'll explain what's going on here with both of these images and why we chose to sort of make the models this way. So the main features of the models, so talking about size and sort of the depth of the tactile features, we settled on models that were roughly the size of a postcard. The advantage of this is they're easy to handle. You can pick them up with one hand, with two hands. You can sit them on a table. Very easy to handle. They're not so big that you have to find a big sort of space to set them down. That was the feedback we got there, was that people wanted something that they could sort of pick up, put down, put on lots of different surfaces. Everyone has a really unique way of sort of interacting with these, and so that allows for that. They're also not so big when they're that size that people get lost in the detail. We found with much larger tactile surfaces, there was often just so much detail in the images that we produced that people would lose track of where they were in the image. They would lose track of the details they were feeling. It was much harder for people to build an overall sense of the tactile features and the shapes of the objects that they were interacting with in the tactile images. Last but not least, the tactile height actually ended up being really important here as well. We settled on 3 millimeters. We found that gave people the best sense of sort of change in brightness from one part of the image to the other. Any taller than that, and the model started to get really sharp and quite unpleasant to feel. Any shallower than that, and people weren't necessarily able to sort of feel those changes in brightness. So yeah, 3 millimeters was sort of the best option there. Looking at the front of the model really quickly, there are a couple of things you might notice. At the top, we have a tactile nameplate. That's a quick way for people to orientate the image, and you'll see why that's important in a couple of slides' time. We also have a raised border around the edge of the image. That's actually as high as the brightest feature or the brightest tactile feature in the image. So it's sort of a way for people to calibrate what they're feeling. If they're feeling any particular part of the model, they can reach over and work out how high that is compared to that border around the edge. So it's just that extra way for people to understand what's going on in the images. If we flick over to the back of the models now, we do have a picture. So this is the original image that was used to make the models. The advantage of having this on the back, and it's mirrored so that it basically corresponds one-to-one with the tactile features on the other side. This allows users with low vision, who've still got a bit of usable vision, or people who have perfect vision who want to use these models, to look at that image while they feel the tactile features on the other side. And so that's just a way for people to use a combination of senses, so sight and touch, if that's something that works a little bit better for them in this context. So I talked a little bit about the importance of good descriptions and analogies. So we realized very quickly, often by making mistakes in the ways that we chose to describe things, that the descriptions around these models, the way we talked about astronomy, was actually really important as well. It didn't matter how good the models were. If we weren't describing them in an accessible way, then they basically weren't worth anything. A couple of examples of how we sort of had to tweak the language we use. So when we talk about color in galaxies, it's really important to actually link that to the physical stuff that the physical processes, sorry, that are producing those colors. So in galaxies, if there's red light, that's normally coming from older, cooler stars. If it's blue light, it's coming from younger, hotter stars. So making sure we made those links to temperature and stars really early on makes the models much easier to understand. We can also link color to the tactile feel of the models as well. So in general, the redder light from the galaxies tends to correspond with much smoother features. The bluer light tends to correspond with much more stark, sort of sharp features. And so people actually build up their own way of talking about the feel of the models based on the color as well. Last but not least, talking about galaxies or things like that themselves, we need to be really careful how we describe a galaxy. So describing a galaxy as like a cloud of stars is a good starting point, because obviously if you've ever walked through the fog on a rainy morning, you have some experience of what a cloud feels like. But we have to be really careful when we use descriptors like spirals to talk about the shapes of galaxies, because not everyone has reached out and touched a spiral. It's not necessarily a particularly easy concept to understand. So we need to think about how to describe a spiral, or use an example like a foil pinwheel as an example of a spiral shape. Okay, so moving on to working with schools. We developed workshops that are appropriate for students in lower primary and upper secondary. The reason we wanted to focus on those age groups is because it's a good time to be inspiring students that age with science. They often won't have completely made up their minds about whether science is for them or not. It's a really good chance for us to come in, show those students that science can be accessible to them, and maybe inspire them to either just pick up an interest in science or go on and study something like astronomy later in life if they really want to. So the workshops are designed to be obviously vision impaired accessible, but we've also designed them to work with audiences outside of that particular target audience as well. And I'll explain that in a little bit. We've also paired the content of the workshops, at least the workshops we run with primary school students, with the space topics that are covered in the UK curriculum. But we then have other workshops that build on those ideas and sort of cover stuff that isn't necessarily covered in the core curriculum. And we really try to build up ideas and concepts in a way that's accessible to blind and vision impaired students. So to make sure all of this was going to work, we did more testing. So we found local schools that had provision for vision impaired students. So that means basically that they're likely to have more vision impaired students in attendance because they have more support and funding for that. But most of these students are embedded in mainstream classrooms with mostly sighted classmates. So we work with those students. We went back and forth a little bit more on the descriptions around our models, how we should structure the workshops, everything like that, just to make sure that they were going to work in the context that we wanted them to. So for our primary school workshops, we always start off talking about the solar system, because the solar system is a topic that's covered in UK schools in later primary school. When we talk about the solar system, we use simple props to talk about the sizes of the planets. We use a beach ball to talk about the size of the sun. We use a peppercorn to talk about the size of the Earth in comparison to that. We use a tennis ball to talk about the size of Jupiter in that scale as well. We then get students to map out the solar system on a long strip of paper using tactile stickers. So in this case, in the picture on the right, we've used rhinestone stickers, so little gem stickers. And that means that students can get a sense of how the planets in the solar system are spread out, sort of get a sense of the scales we're talking about when we talk about the solar system. We then come back and do a second workshop where we go beyond the solar system. We talk about larger scales, our Milky Way, and things outside of our Milky Way. So we start off by talking about the night sky and constellations. And on the left, I've got an image of a simple tactile model of the constellation Orion. We then have a tactile model of an image of the Milky Way, so we can talk about how we view the Milky Way from the inside. We then get students to build their own model of the Milky Way using a CD and some Play-Doh. That serves two purposes. It gives the students a sense of how our Milky Way is sort of shaped in a 3D sense, but it also sort of almost trains students to start feeling those spiral shapes that are going to be popping up in a lot of our more complicated tactile images. Once we've talked about the Milky Way, we can then talk about other galaxies, and we have a set of 10 galaxy images. They're all really different galaxies. They all show very different things. We get students to explore these and come up with their own galaxy classification scheme. So it's very much up to them as to what they do here. There's no right or wrong answer. It's a good chance for them to explore the model, see what they can feel. And last but not least, if we have a little bit of time to spare, we can talk about color in these images as well. And the way we've dealt with color is we've taken telescope images that focus on bluer or redder wavelengths, and we've basically made models of both of these. So the one on the left here is our red light image. The one on the right is our blue light image. And you can see that those are highlighting really different features. We then have a version of this Galaxies workshop for students in lower high school that deals with slightly more complicated concepts. We talk a little bit more about what actually makes the galaxies the shape that they are, what's going on with the gas and the stars inside those galaxies to give them their shapes, and also how galaxies evolve and change over time. So how we can go from something like a spiral galaxy to an elliptical galaxy. Spirals are like the ones in the image here. Ellipticals are our big plain looking galaxies with not too much detail. Okay. So I want to finish off by talking about how we deliver the resources. So there's sort of two modes that we focused on, and they both have their pros and cons. The first is classroom delivery. So the advantage here is that you can often end up working with small numbers of vision impaired students, but alongside lots of sighted students. The advantages here is that we can get everybody working with the same resources at the same time. And so this can actually lead to the vision impaired students feeling more included in the class than they would normally. So a lot of the time, VI kids are sitting off to the side doing something slightly different, often with adaptive technology. The advantage here is that everyone's using the same accessible resources to do the same activity at the same time. So everyone feels included. We found that this can break down barriers. It can get students talking to each other. It can help the sighted students understand what the VI students actually need to do to sort of adapt to regular classes. So we've seen quite positive outcomes there. The only issue here is, of course, that it requires large numbers of resources to run well. And that can be difficult, particularly if you have to 3D print this stuff yourself. It can also make it more difficult for the VI students to ask questions, just because there are so many other students doing the same activity at the same time. The second mode of delivery that we've focused on is a slightly smaller scale, I guess. It's where we work with maybe an individual student or just a small group of vision impaired students. So obviously the major advantage here is this feels more personal. The VI students are much more likely to ask questions. It also requires a much smaller number of resources to run well. It does also mean that we can take our time a little bit. It means the VI students don't feel like they're being rushed. They can really explore the models. They can ask lots of questions. Yeah, this mode also works really, really well. Finally, I just wanted to finish with a really important point, and that's the importance of enabling rather than directing. So even though with these models, it can be really tempting to sort of guide the students through what they should be feeling in the models, to tell them everything, to try and make them find the features and the stuff in the models that you want them to find, that actually can produce, I guess, an experience that isn't as rewarding for the students. So the way these models work best is with minimal guidance, but letting the students discover things on their own, letting them tell you what they found, and then letting that guide your discussion about what's going on in the image or what's going on in the particular model that they're feeling. This can really empower the students. But yeah, it allows them to be independent. You're basically not taking away their independence by giving too much of a curated or guided experience. Okay, last but not least, if you've enjoyed this talk, if you think Tactile Universe is maybe something you'd like to get involved with, all of our resources are actually available for free to download from our website, which is www.tactileuniverse.org. You do need access to a 3D printer, obviously, to produce the models, but we've also got copies of all of our lesson plans, all the stuff that we use to sort of deliver our workshops. And if you ever need to get in touch with us, you can reach us at tactileuniverse@gmail.com. Thanks so much for listening today.